Okay, so I will continue to give proof of proposition 7.4.b, and we have completed the proof of part 1 last Tuesday. And there's a correction that last Tuesday I state that if expectation of x exists and is finite, then E of y, the expectation of y exists and is finite. But this is incorrect in general, so I have to correct it. We can just make sure that the expectation of y exists. Okay, but we still have this inequality. Okay, so please correct the statement here. Okay, and I will explain why the expectation of y may be minus infinite. Okay, so it is possible. Yeah. Okay, so let's see the second part. Okay, and I think I have right. Since x greater than or equal to y with probability 1, okay, so there is an event omega 0 in the sigma algebra F that with the probability of this event omega 0 is equal to 1, such that the value of random variable x will be greater than or equal to the value of random variable y for all outcome in this event omega 0. Okay, all right. So now for any outcome in omega 0, we have that the positive part. So if the positive part of y at omega is positive, then by definition we know that y omega is positive. Okay, it's by the definition of positive part. Okay, and so which means that x omega will be greater than or equal to y omega, and which is positive. Okay, because we know that for any outcome omega in omega 0, we have this inequality. So if this is positive, then of course x is positive. And so this implies that the positive part, because x omega is positive, so that x omega is equal to x positive part, okay, will be greater than or equal to, okay. Right, so we have that. The other possibility is, and if the positive part of y at omega is 0, then of course so that we know the positive part always non-negative, and this is equal to, okay, right? So So both of them shows that x plus omega is going to equal to y plus omega for all omega in omega 0. That means that x plus greater than y plus with probability 1. Okay. So we first show that x plus is greater than or equal to y plus with probability 1. Now, and for any omega in omega 0, we have x minus omega greater than or equal to, which implies that, so if the negative part of x at omega is positive, which means that x omega must be negative by definition. Okay? And so this means that the y omega, okay, so y omega also negative. Why? Because for all omega in omega 0, we have this inequality. Okay? So now both y and x are negative, which makes it y minus, okay, will be greater than or equal to. So we know that this is equal to minus, okay? Right? So this is greater than or equal to minus, okay? And this is equal to okay? So we have y minus greater than or equal to x minus. And when x minus omega is 0, then which means that y minus omega, which must be equal to 0. And we know this is, okay, so we achieve the same inequality. Right? So which shows that by the way, we'll show that. I'm sorry. Okay? If I think we have two statements here. So which show that y greater than or equal to x minus omega for all omega in omega 0. So which means that y minus is greater than or equal to x minus with probability 1. All right, now this implies that expectation of x okay by part 1, because we have two non-negative random variables, and we know we have this inequality with probability 1. So by part 1, right, we have this inequality. And similarly, it's implied that expectation y minus greater than or equal to expectation of x minus, okay, by part 1, 2. Now we use this condition. Since expectation of x exists and is finite, right? So since expectation exists and is finite, okay, if and only if, now, maybe I will say, now, if and only if the positive part is finite and has expectation, and the expectation of its negative part also finite. Okay? In chapter 5, we know. So once we know a random variable has finite expectation, then the expectation of its positive part and negative part are finite. Okay, so we have that. Now, because the expectation of x, the positive part of x is greater than or equal to expectation of the positive part of y, so that this implies that expectation of y plus is finite. All right, and then, so expectation of y exists. Okay. But expectation of y minus here may be infinite. Okay, even though expectation of x minus is finite, as we know, but because this is greater than this one, so it's possible that this expectation is infinite. And in this case, the expectation of y is minus infinite. Okay, so we just know that the expectation of y exists. Okay, but maybe minus infinite, maybe finite or maybe minus infinite, but cannot positive infinite. It's impossible. Okay. All right, and so now we have the last one, the inequality to prove. All right, so that the expectation of x is the expectation of x plus minus the expectation of x minus here. So it is greater than or equal to expectation of y plus, okay? Because expectation x plus is greater than expectation of y plus, minus expectation of y minus. Because expectation y minus is greater than or equal to expectation x minus. So you subtract more. That's why you have a lower bound. Okay? And this is just, okay? And this complete the proof. Any questions? Okay, so if no question, now I will present next proposition, which is useful in the proof of Schwarz inequality. A random variable z is equal to 0 with probability 1 if and only if the second moment of z is 0. Okay. The forward direction All right, so with the probability that z equal to 0 is 1. All right, so this event, z equal to 0 with probability 1. All right. So we have that expectation of z square, okay, is equal to z probability of z equal to 0, and which is 0. Okay. Okay. So the forward part is very easy. Okay. Or if you want me to do it gradually, this implies that probability. Okay, this is so z equal to 0 is probability 1. If only if z square is equal to 0 is probability 1. All right, and so the expectation of z square is equation of z. Okay. Remember, by the remark, after proposition 7.4.8. Okay, so if two random variables are equal with probability 1, then they will have the same expectation. Okay, if one of the expectation exists, right? We know that. So, but zero, the zero random vector has expectation, of course, which is 0. Okay, so and so this is 0, of course. Right, so this is a very precise proof. Okay. Now the reverse direction, so we know that the second moment of z is 0. Then we want to show that z is equal to 0 with probability 1. So we first show that the probability that z greater than 1 over n is 0 for all n in the set of all natural numbers. Okay, so we first show that. Okay. Right, so suppose, so we prove this by contradiction. Suppose that, there exists a positive integer n such that the probability that the event that the absolute value of z is greater than 1 over n is 0, it's positive. Okay, so suppose this is not true. This is not, which means that there exists an integer, a positive integer, such that this event has positive probability. Okay, suppose we have that. Now things. So this square is greater than or equal to z square times the indicator that z square greater than 1 over n square. Right? And this event is equal to this event. Right? So we say the absolute value of z greater than 1 over n, if and only if the z square is greater than 1 over n square. Okay? So they are the same. Okay. Okay, so this is the indicator. And we know indicator has value equal to either 1 or 0. So we have this inequality, of course. Okay? And but for omega such that this is 1, we know z square is greater than 1 over n square, so that this has the lower bound. Okay? So you can replace this square by the lower bound here. Because if this square is greater than 1 over n square, less than, if this is less than or equal to 1 over n square, the indicator is 0. This is 0. Okay? So that so we have this lower bound. So let's say where the indicator of the event which is equal to right, so we have that, and so we have that the expectation of z square. Okay, so now we know this is the non-negative random variable. This is also non-negative random variables, and so we can apply the part 1 of proposition 7.4.b, right? So the expectation of this square is greater than or equal to the expectation of 1 over n square, and the indicator of z square minus greater than 1 over n square. Okay? Right? So this is by proposition 7.4.b-1. Okay? The part 1 of the previous proposition. Okay? But by the linearity, this is n square, expectation of the indicator of this event. Okay? So this is by the linearity of expectation in proposition 7.2.a, right? So in the section 7.2, we have show the linearity of expectation. Okay, so we have that one. But this is 1 over n square, and this is the probability that this square. Okay, so we have shown that the expectation of the indicator of an event is equal to the probability of that event. Okay, so this one. All right, and now, so this is positive. Why? So this is equal to and this is positive, okay? Because we have assumed that this is positive. Now, so when when this is positive for some n, we have shown that the expectation of this square is positive, right? Which is a contradiction to, but we know the second norm of z is 0, so it is a contradiction. All right, so this assumption is not true. We can't have any positive integer such that this event has positive probability. This is not possible. Okay, so we have shown already here. Okay. Right? So now we have shown that this is true. Okay, now since this is a sequence of it's an increasing sequence of events. Okay? Because as n become bigger and bigger, the event become bigger and bigger. And so that its limit is just the union okay? And what is this limit? Which is just the z not equal to 0. Okay? I have to say, right? As n goes to infinity, the increasing sequence of event has the limit, which is the union. Okay, and you will see that this is the okay. Okay, if you need a proof, well, you will see that omega in the event. Okay? If and only if okay? If this is a number which is non-zero, we can always find an n, right? Such that the absolute value of z is greater than 1 over n. Okay? All right, and so this says that omega is in z greater than for some and in n. Okay? For some, so it means that omega is in the union of this event. Okay? So omega in this event, if and only omega in this event, so which shows that these two events are the same. Okay. Right. So we have this one. Okay. Now by the continuity of P, right? So the limit of the probability of the event here as n goes to infinity is equal to the probability of the limit of okay, and we know this is equal to the probability that the union okay, and this is the probability that z not equal to 0. Okay. But what is this? The direction is limit n goes to infinity and 0, right? Because we have shown this probability always 0. So that so we go this way. So it's 0. So probability of this event z is 0. So that probability that z equals 0 is equal to 1. Okay, so we complete a proof here. Okay, i.e. z equal to 0 with probability 1. Any questions? Okay, so if no question, then I will present Schwarz inequality. Right? So let x and y be two random variables with finite second moment. I.e. Okay. Then x times y, then the expectation of x times y exists. And it's finite. And the square of this expectation has an upper bound, which is the product of the second moment of x and second moment of y. Right, so this is the so-called famous Schwarz inequality. Okay, and the equality holds. Okay, so the equality holds if and only if y is equal to alpha x or x is equal to beta y with probability 1 for some constant alpha beta. Okay, so in the statement I also give if an only if a condition for the Schwarz inequality becomes to be equality. Okay, so now we give a proof here. We now consider special cases. If the second moment of x is 0, right? So if the second moment is 0, then x is equal to 0 with probability 1. By proposition 7.4.c, we just proved. Okay, so we know that. Thus, x times y is equal to 0 with probability 1. Right? Because x is 0 with probability 1, so x times y is 0 with probability 1. So that the expectation of x times y, so this expectation is 0. So even though we put the square here, it's also 0. And so this is 0 square and 0 times okay. So now we have equality, right? We now have equality. And we know that x is actually equal to 0 times y with probability 1. So the beta, we have a beta which is 0, right? Because we reach the equality here. And to reach an equality, either this or that, right? Either one. And we in here, in this case, we have beta is equal to 0 here. Okay, so for this case, the other case is if the second moment of y is 0, then y equal to 0 with probability 1, again by proposition 7.4.c. Okay, so that's x times y is equal to 0 with probability 1. So that's again right? So now the Schwarz inequality becomes to equality. And we know that with probability 1. Okay. So we have this relationship that so y is 0 times x. So now we now assume that both second moments are positive. Okay? Both second moments are positive. So maybe I will add one so that okay, we need this one because we need exists and is finite. Okay, so this expectation exists as finite. Actually, its value is right. So please add. It's true. Right? Now, we assume this case. So we first prove that this expectation exists and is finite. Okay? So we first prove, right? The product of x and y exists and is finite. To show that, we let x prime to be x, but divided by the square root of the second moment of x. All right. Now we are able to put the square root of the second moment of e in the denominator. Why? Because, yeah, right. And y prime defined to be y divided by. Okay. So we have that. Now we use x, and so then x prime and y prime have finite second moment. All right? So they have second moment, and with square equal to 1. Okay, so their second moments are equal to 1. Okay, so if you take the square here and take expectation, okay, and so by using the linearity of the if you need a proof with okay, so here is the linearity of expectation equal to 1. Okay, so both of them are 1. Okay. Now, since x prime plus minus y prime square always greater than or equal to 0, right? And so this implies that x prime square plus y prime square greater than or equal to plus 2x prime y prime. And so this implies that x prime square plus y prime square greater than or equal to 2 to take the absolute value here. Is that okay? They are functions, right? They are real. This is real value function. This is also real value functions. And so the sum of the square of these two functions is going to the plus or minus of 2 times the product of these two functions. Okay? And so because it's plus or minus either one, so we can take the absolute value. Now, the left-hand side is a non-negative random variable. The right-hand side is also a non-negative random variable. Now, by proposition 7.4.b part 1, so we have that expectation of okay, maybe I write this way. So 2 times the expectation. So this is by proposition. Dash 1, part 1. Then by linearity of expectation, so it's 1 plus 1 equal to 2. And here is equal to this one. Okay. And by the linearity of expectation. So, which means that expectation of less than or equal to 1. Now, since x prime, y prime is equal to x times y divided by the square root of expectation of x square. Okay. Okay. From the definition of x prime, y prime, so their product is equal to this one. Right? And so when we do the substitution here, so we have that the expectation of So this is implies that and which is finite. All right, so this shows that expectation of xy exists and is finite. Okay? That you have to know this is equal to expectation of the positive part of the product plus the expectation of the negative part of the product. Okay. All right. So this expectation is finite means that the positive part of x times y is finite. The negative part of xy is also finite. Okay. So their difference is finite. That just means that the expectation of xy exists and is finite. Okay. So we have shown the statement here. Okay, the statement. Now we will show the Schwarz inequality. Now, since we know that the expectation of x minus okay, so we consider that the expectation of the square of this difference. Okay. And we can construct this difference because we know the numerator is finite, okay? Exists and is finite. Right? So that we can consider this difference. Okay? This is the reason why we need to show that the expectation of x times y exists and is finite. Okay, otherwise we can't consider this inequality. Okay? Is that okay? Now here. Okay, and now we can compute it. So this is actually equal to expectation of x squared minus 2 times this ratio okay, and the expectation x times y plus the expectation of, I will 2 here. Okay, it's here. And this is equal to, and here is 2 of the square divided by expectation of y square. And plus expectation plus the square Okay, because the numerator is the square of the expectation of y square. But now we have expectation of y square, so we cancel one of them. And then we have this one. Okay, so that this is expectation of x squared minus expectation of x times y divided by expectation of y squared. Alright, so 0 is less than or equal to this difference. Okay, so that expectation of x times y squared divided by e y squared less than or equal to expectation of x squared. Okay, and so now we have square less than or equal to. Alright, so this is the Schwarz inequality. And the equality holds. So equality holds if and only if that x minus equal to 0 is probability 1. Okay, by position 7.4.6. Okay, so we have equality 0 is equal to this expectation if and only if the difference is 0 with probability 1. Okay, so that is from proposition 7.4.6. Okay, so which means that x is equal to a constant times y with probability 1. Okay, but this is actually equal to with probability 1 for some non-zero constant beta. All right, so if this is true, then of course the forward direction, you can let beta to be this constant, right? And this constant must be non-zero. Why? Because if beta is 0, then x is 0 with probability 1, which is a contradiction to the assumption that that the second moment of x is positive. Okay, so that beta, if we get this beta to be this number, then of course it's a constant and it's non-zero. Conversely, if x equal to b, so okay. And I show that if then the expectation of xy divided by is equal to beta. Okay? Is that okay? So beta is exactly the ratio. Okay. So if you want a proof, this is a simple proof. Okay. Okay, so this complete the proof. Okay. Any questions? All right, so we'll take a break up to 2:35. Now, I will restate proposition 7.4.1 in the textbook. So if x and y are independent random variables, then for any Borel measurable real valued functions G and H on R, the expectation of G of X times H of Y, okay, is equal to the expectation of G of X times the expectation of H of Y. In particular, if X and Y are independent, then provided that okay, in particular, if X and Y independent random variables, then EXY equal to provided that and the proof actually so this is just part 2 of proposition 7.2.b. Okay. So if you you see we have proof proposition 7.2.b. Okay. And we have 2 parts. The first part deals with non-negative random variables. Okay. And for non-negative random variables, we know their expectations always exist. Okay. And so that we have this identity. But for general random variables, we require that their expectations exist and are finite. Okay, so we have that, And in this proposition, you know that the expectation of their products exists and finite, right? Provided that both expectation exists and finite. So we do not require that x and y has finite second moment. Not like in the statement of the Schwarz inequality, because in the statement of the Schwarz inequality, x and y may be independent or may not be independent, right? So this is general. But if x and y are independent, if they are independent, then the existence and finiteness of the expectation of this product is guaranteed by that the existence and finiteness of their expectation only, the first moment. All right. So this is very special for independent random variables. Okay. So I restate proposition 7.4.1 in the textbook carefully here. Okay. You know that my statement is very precise. Okay. And of course, if G and H are non-negative functions, then the provision is not necessary. Okay? Just like here, if both x and y are independent non-negative random variables, then this is also automatically true. And we don't need expectation x, expectation y to be finite. We don't. Okay? Any of them can be infinite. That we still have the identity here. Okay. We recall that proposition 5.2.L a random variable x has a second moment then if a random variable x has one, then x has a finite mean or first moment, okay? Okay, so if you have a higher second moment, then you will have a lower first moment, right? This is in proposition 5.2.L. Of course, in proposition 5.2.L, the fourth statement is that a random variable has a finite second moment if and only if it has a finite mean and it has finite variance, right? So that this is stronger, but we just take a part of the result in proposition 5.2.L. And this one can be generalized in the next proposition. E. So let x be a random variable. If 1 is less than x, less than r, and we know that the expectation of x, the rth power of absolute value of x is finite, Then the S power of the F value of X has a finite expectation too. Okay. And both X and R should be greater than or equal to 1. Okay, so this is true. Okay. Okay, so the proof, okay, I think I asked an exercise for you. Okay. And actually the proof is the same as the proof for the first part in the proposition 5.2.L, very similar. So I think I will make up an exercise for you. All right, now the covariance, now we define the concept of covariance between two random variables, X and Y, with finite second moment, denoted as COV of X, Y, is defined as the COV of X, Y is defined to be the expectation of the product of X minus the expectation of X and Y minus the expectation of Y. Okay, and the existence of covariance require that X and Y have finite second moments. Okay, because that in here, as we know that we can show it. So this is X times Y minus E minus E. Okay, plus okay, so it's this expression. So if you multiply these two factors out, you get 4 terms here. And because X and Y have finite second moment, so by Schwarz inequality, that the product of X and Y has finite expectation. So X times Y has finite expectation. And so here, so we can write down okay, so this is by Schwarz inequality. Or just by proposition. Seven 7.4 and the linearity, so position, linearity of expectation stated in proposition 7.2.8. All right, so we have that. And then we cancel them. So the covariance can be computed as here. Okay? Right, so the covariance of xy is equal to the expectation of x times y minus the expectation of x times the expectation y. Okay, so that is the covariance there. Now, if x and y are independent, then we know that the expectation of x times y is equal to the expectation of x times the expectation of y. Okay, by proposition 7.4.1. Okay, right. So because x and y has finite second moment, so they have finite first moment, as we know, and we have that. So that the covariance of x and y become to be 0. Okay, so if x and y are independent, then their covariance is 0. But covariance of x and y is 0 does not imply that x and y are independent. For example, consider a random variable x with the following distribution. Okay, so it is equally probable with 3 possible values, 0, 1, 2. Okay, so x is the discrete random variable, and consider a random variable y defined by so the y is 0 if x omega is not 0, but if x omega is 0, then it's 1. So that this is actually the indicator of x equal to 0. Okay? So y is just a function of x. Okay? It's a function of x. Okay? So it's the indicator of the event. Okay? Now, then x times y always equal to 0. Okay? So that the expectation of x times y is 0. Okay. Now, since By the way, I forgot. No, it's -1, sorry. Not 2, I'm sorry. So x equal 1 minus 1 here. Now the expectation of x is equal to 0 times 1/3, 1 times 1/3, plus minus 1 times 1/3. Now the expectation of x is 0 here. Okay. So we have the covariance of x, y. Which is 0, okay? So x and y has 0 covariance. However, but we have say that probability that x is equal to x equal to the joint probability, say x is equal to 0. Okay, y equal to 0. Y equal to 1, which is equal to probability of x equal to 0, so it's 1/3. Okay, but this is not equal to okay? Because the probability of x equals 0, okay, is 1/3, and probability y equal to 1. Y equal to 1 means that the x equal to 0, okay? So that they have 1/3. Okay. Implies that x and y are not independent. Okay. Right. So this is a very simple example to illustrate that even two random variable has 0 covariance, that x and y may be or may not be independent. Okay. So independence is much more stronger than 0 covariance between two random variables. Okay, the next proposition says that if x and y are two random variables with finite second moment, okay, with finite second moment, and A, B in R, then the linear combination of x and y by the two coefficients A, B, right, So this is a new random variable, right? This new random variable has a finite second moment. Okay. Okay. In proposition 7.2.b, in A, we show linearity of expectation, right? So about the first moment. So if two random variable has first moment, finite first moment, then any linear combination of x, y also has a finite first moment, and we have the identity, right? As stated in proposition 7.2.8. And this proposition says that if x and y have finite second moments, then their linear combination also has a finite second moment. Okay, but we don't have an explicit expression, okay, because this is a nonlinear function. Okay, so of course you know that how to compute the second moment of this linear combination. It involves the expectation of x times y. Okay, all right. Now, okay, so the proof is also as an exercise. Okay, for you. All right, so now we will state proposition 7.4.2 in the textbook. So it consists of 4 parts. Covariance of xy is equal to the covariance of yx. So covariance function is symmetric on its arguments. Okay. The second thing is that the covariance of x with itself is just the variance of x itself. Third, covariance, okay, of a scalar multiple of x and a scalar multiple of y is equal to, you just move out the 2 multiples. All right, so it's a times b of the covariance of xy. Okay, and the fourth, covariance of the summation of xi's and a summation of yj's. Okay, so suppose that each argument is a sum of random variables. Okay, now it is equal to the double sum of the covariance of xi and the yj. Okay. So in here, so let x, y, x1 up to xn, y1 up to ym be random variables with finite second moments. Okay, so all the random variables involved here, we assumed that they have finite second moment. Okay, so for that, so you have this one, and the proof. Okay, I think that's simple. So the proof as an exercise 2, right? Because they are so simple to have. Okay, so an application of proposition 3.2-4, the first one, the variance. So if we want to compute the variance of a sum of finite number of random variables with finite second moment, now we know this is covariance of and a second. All right. So when you write down this sum, you should use different indices. All right. Don't use the same index, otherwise you will get into troubles. Okay. All right, and so that we have covariance of xi, xj here. Okay, and so this is I from 1 to n, the variance of x sub I plus 2 times the summation of I less than j less than equal to n, the covariance of xi and xj. Here, okay? So in here, I is less than j. Okay. So you have this formula, and in particular, if xi's are independent, then we know that covariance of xi, xy is 0 for all I not equal to j. Okay? So that the variance of their sum is equal to the sum of their variance. Okay. If x1, x2 up to xn are independent random variables. Okay. So for independent random variables, the variance of their sum is equal to the sum of their variance. Okay. If they are not independent, then you have to use this formula here. Okay, so they are different. Now, an application of Schwarz inequality gives us an inequality for covariance. The G for any two random variables x and y with finite second moment, we have the square of the covariance is less than or equal to the variance of x times the variance of y. And equality holds if and only if either y is a linear function of x, so that x alpha times x plus a theta constant, or x is equal to beta y plus gamma. With probability 1, okay, for some constant alpha, beta, gamma, delta. Okay. Okay, so let's see the proof. We let z to be x minus the expectation of x, and w defined to be y minus the expectation of y. Right? So by Schwarz equality, all right. So by the Schwarz inequality in proposition 7.4.d to z and w, okay, we have that the covariance of xy, the square, we know this is expectation of x minus e, x times y minus ey. Okay, so this is the expectation of z times the square, right? Right, so we apply the Schwarz inequality to z and the w. So this is less than or equal to the square times the expectation of the square. Okay, so here is the Schwarz inequality, and for here we have the expectation of okay, but this is exactly the variance of x and the variance of y. Okay, so we have shown this inequality. The square of the covariance of x and y is less than or equal to the variance of x times the variance of y. Okay, and the equality holds if and only if that c is equal to x minus ex, which is equal to okay, maybe I stated it the other way, that y minus e y, which is w, is equal to alpha z or okay, with probability 1 for some constant alpha, beta. Okay, and now, so this is if and only if y equal to alpha x plus theta, or x equal to beta y plus gamma with probability 1 for some constant alpha, beta, gamma, and delta. Okay. So you know what is data here? The data actually is expectation y plus alpha times expectation x. Okay. Okay. So you have this one. Any questions? All right, so if no questions, then I stop here.